Hello everyone, I hope you're doing well. Just before we get into the weekend, we have one more note that we need to go through this week, and it's about graphical differentiation. We're going to look at this more next week when we talk about higher order derivatives, but for today, we're just going to be looking at general sketches of derivatives of functions. And to go about doing this, there are three main things that I personally look at in order to do these rough sketches. So when you see a function, the first thing I personally look at is where are their horizontal tangents? So in other words, where is the slope equal to 0? Where do we have a 0 slope tangent line? And these values of x correspond to the x-intercepts for the f prime function. Okay, so for the derivative function. So in other words, y is equal to 0 and then somewhere along the x-axis. The next thing I look at is where is f of x increasing? So in other words, where is there a positive tangent? If you were to take your pen and put it against a function, where is it facing upward, positive slope? And then where is there a negative slope? Where is our function decreasing? Now in terms of plotting your derivative, wherever the function is increasing, going upward, we plot that in the positive y-axis for our derivative graph. But if we have our function as decreasing, regardless if it's decreasing in the positive y or negative y region, when we plot the derivative function, that will correspond to the negative y region. Okay, and you'll see what I mean in a second. But first, before we look at general graphs, let's first start with something that we're a little bit more familiar with. Okay, so let's start off with a cubic function. Again, I'm just going to put 1/3, so when I differentiate, it'll just be a little bit easier to have the standard parabola. But let's say we have a cubic function. If we look at its derivative by power rule, this gives us a parabola. If I take the derivative of a parabola, it's going to give us the equation of a line. If I took the derivative of the line, I would get just a constant, so a horizontal line. Okay, so we're going to take a look at these, and we are going to plot them. So the first one, our cubic function, will look something like this. Okay? Now, where along here do I have slope is equal to 0? So I can draw a horizontal tangent right at this point. Let me zoom in a little bit. Right at this point right here. Okay, so that corresponds to a horizontal tangent line. Now, what I do is I like to put my graphs right underneath each other, because wherever there's a horizontal tangent line, that corresponds to an x-intercept. In this particular case, it's happening at x is equal to 0. So I know that my function, my f prime function, when I draw it, it's going to have to go through this point. Now, we know what a parabola looks like, right? In this case, we know, okay, it's just going to look something like this. But how would we figure that out if, we didn't know what this function was? Let's just say we completely forgot. Well, we know that f prime has to cross this red point. Now, let's look to see where the original function is increasing or decreasing. Now, in this case, even though we're in the negative region right here, our function is increasing. Okay, it's positive. So when I plot my derivative function, that means that the lines are going to have to be somewhere in the positive y-axis, okay, where the function is increasing. Now, also, here, our function is also increasing. So again, it would mean that in this region for our f prime, we would have to be in the positive y region. So in this case, in order to touch this point, but always be in the plus area, that's why it makes sense that it goes down, but then it stops at this point, and then it goes back up. But we're always positive. Our derivative is always positive. It's always going, the function's always going up. Always has positive tangents. Now, same thing again. Except now let's think about this function as the function we want to take the derivative of. Okay, really this is f double prime, but let's just focus now on this one. So again, I'm going to start off looking at where do I have a horizontal tangent. Now it just so happens again, at this point, we also have it at x is equal to 0. So when I plot the derivative of my parabola, I'm going to have to go through this red dot here. Now, in this case, we have that our function from negative infinity to 0, it's going downward. Okay, if I take my pencil, I see that if I draw tangent lines, they're all facing downward slope direction. But then over here, from 0 to positive infinity, our function's increasing. So for the plot of my derivative on the right side here, okay, I know that my function, my derivative function that I need to draw is going to be somewhere up here, okay, because we need to have it in the positive region. And then for the left-hand side, for the negative x values, I'm going to have to be down here because my function is decreasing. Okay, now it turns out that this is a line, so we know that it looks something like this. Okay, so I know that, but that's why it makes sense. This corresponds to the spot where the function's going down. These spots correspond where the function is going up. And then finally, if I were to take the derivative of this function, note that this is a positive slope. Okay, so this is always increasing. This is always going upward. And we know that for a line, if we differentiate it, we just get a constant value. Now, because we're increasing, we're going upward, when we draw the derivative of this line, it's going to have to be in this positive area here. Okay, so it would correspond to whatever the slope, whatever the slope of that tangent line is. Now in this case, I think it's actually 2. It would be 2. So this value would correspond to m is equal to 2. Okay, but again, the reason why that line is there is because the slope of the linear function is positive. So since the slope of linear function is positive, our horizontal line is above y is equal to 0. So our horizontal line is above y is equal to 0. If we had a negative slope, so if our line looked like this, for example, we would have to draw its derivative down here. Okay, constant function that's negative constant. Okay. Okay, so there's that example. Now just to illustrate this, so as I was saying, if we have a positive slope for the equation of a line and we sketch its derivative, whatever this actual slope value is, whatever that m is, when we plot its derivative, it'll be somewhere here. Okay, so that will be m, whatever m is. You know, say it's 2, then that would be 2. But in this case, if I were to differentiate this, I would just get whatever negative m is, the negative value for m. So if I were to draw the derivative of the function here on the right, it would just look something like this. Okay, where this corresponds to negative m. Now, if I differentiate a constant, what do I get? I get 0, and I would get 0 at every point. So if I differentiate here, I would get 0. If I differentiate here, I would get 0. Here I get 0, so on and so forth. So when you differentiate a horizontal line, it's just going to give us 0 for every single x value. So if we were to draw it, it would look like this in this case. And then it would also be along 0 for this function as well. Okay? So when we sketch the derivative of just a constant, we just get a line 0. Okay? Because we have 0 at every single point. Alrighty. Now just a quick little remark about terminology. And again, we're going to formally define these things next week. But when we have positive derivative. So in other words, the slope of the tangent line at a certain point of a function is positive. So say look at this function, for example. If I draw a tangent here, it's positive. If I draw a tangent here, it's positive. If I draw one here, it's positive. In those areas where you would have a positive tangent, we say that the function in these regions is increasing. Similarly, in the spots where we have f prime is less than 0, so if you were to draw a tangent line at a point, okay, and it goes downward, so like here, for example, or here, we say that the function in those regions are decreasing. And then when our f prime is equal to 0, so in other words, when we have a horizontal tangent line, the x value that this occurs at, this is called the special point. This is a critical point. And again, we're going to formally define this next week, but just so you start getting used to the terminology. And at critical points where there's a horizontal tangent, they correspond to peaks or valleys, so maxes or mins of the function. So this is a peak, a mountain, it's a type of maximum, and here we have a valley, it's a type of minimum. Okay? Now let's do a few more examples of just more general functions. You don't know what the function is, but you're just given this graph and you want to plot its derivative. So again, the first thing that I personally do is I look to see where my tangent is going to be horizontal. So I'm going to have a horizontal tangent here, and I'm going to have a horizontal tangent here at these points, right here and right here. So I'm going to line this up with my derivative graph because at this x value, whatever it is, that's where I'm going to have x-intercepts. Okay, that's where my derivative is 0. So that's why we're on y is equal to 0. Now, I have to sketch a curve that is going to go through this point and go through this point. Okay, maybe it'll go like this, or maybe it will go like this, or like this, I'm not sure, but it has to go through each of these points. Now, to figure out where we're positive and where we're negative, let's take a look at what's happening to the function. I usually start off with somewhere for points in the middle, just because it's, at least for me, a little bit easier. Sometimes when you're at the end here, it's tricky to be, oh, does it go like this or does it go like this? So let's look in between these two red points. So my function between those red points here, it's going downwards. Okay, so the function is decreasing there. So that means my derivative is going to be negative. So it's going to be in this area right here. Now, in order for me to connect smoothly between these two dots here, I'm going to have a little cup like this. Okay, I know I can't do something, like this, because this would be a corner or a cusp, and things aren't differentiable there. So it can't do anything like that. It has to smoothly connect between these 2 points. Okay, and the only way to do that is to basically draw this cup. Now, how far down does this go? Well, that's actually going to correspond to where the second derivative is 0, but we're going to talk about that next week. Okay, so it looks something like this in general. Now, let's look to see what happens on the right of this and on the left of this. So our function, let's first look on the left. So our function from here to this first red point, this is going upward. Okay, these are positive tangents if we were to draw them. So this is a plus here. And the same thing with here too. Okay, our function is also positive in that area. So that means that in our graph, on this side of the green line, we're going to have to be somewhere up here. And on the left of this first green line, we're going to have to be somewhere up here in the positive y region as well. So the only way to draw a smooth line with no corners, no discontinuities, that's going to connect to this orange part and go through these red curves, is if the line does something like this. And then something like this. And that kind of makes sense because I have 1, 2 red lines here. So this would correspond to some type of weird cubic. And then I get some sort of parabola. So it makes sense. All right, so that's our first example. Now let's do something that looks kind of weird. Now the first thing that sort of stands out to me is that, okay, so I have straight lines. These are just linear, right? This, and this separately. These are all linear. So if I differentiate a linear function, I'm just going to get a constant. So my derivative for here to here will be some sort of constant value. My derivative from here to here will be some sort of constant value, so on and so forth. But I have a little bit of a problem. These little spots here, these are corners, right? And even though our function is continuous with corners, our f prime does not exist at corners. So what happens then? So these are going to correspond to holes in our derivative function. Holes, open holes, because these values can't be included in our derivative, because our function is not differentiable with these three little pink dots here. Okay, now because the slope for, say, this line, this line, this line, this line are all different, not only are these values here going to correspond to holes, but we're going to have these jump discontinuities. So let's not worry about that quite yet. Let's just first sort of get things set up here. So I know that somewhere at this x value, and then at this one, and then at this one, our derivative function is not going to exist. So we're going to have holes somewhere along these green lines. Now, let's look to see where this piecewise function is increasing and where it's decreasing. So it's decreasing the first part, the first line here. While this is negative, this is going down. Same thing right here. This is also negative. So that means that that value, that slope value, it's just going to be a straight line and it's going to be in the negative region. So from here to here somewhere, I'm going to have a straight negative line, and from here to here, I'm going to have a straight negative line. Now, what value is my straight negative line, my horizontal line? Well, this slope roughly is 1, negative 1. So our horizontal line, the derivative of this here, is just going to be a line at negative 1. Again, I'm going to ignore what happens at these green bars here. And then if I look at this other part that's decreasing, the slope is actually the same as the slope here. So we would get a line at that same value. Now, these other two little regions, okay, so in between these two pink points, and then after this last pink point here, our tangent, if we were to draw it, would be increasing. Okay, so our function is positive there. So that means when I draw my derivative term, I'm going to have to be in the positive y region. Now the slope here, again, is actually roughly about 1. So in between these two pink lines, I would have a slope of 1. Okay, something that looks like that. But this other part where the slope is positive, after that last pink point, this is not nearly as steep here. Okay, so notice here that the slope here is not as steep. Okay, so let's say it's roughly half the slope of this first line that's increasing. So that means when I plot my derivative function, okay, it's going to be at roughly half. All right, that's great. Now, what happens at these spots here where we have these discontinuities? Well, we can just put holes at the end of each of these lines. And remember, they're open holes because they're not included in our derivative. So I would have a hole here, I would have a hole here, I would have a hole here. And these would be jump discontinuities, where then these green lines, I have these holes. So we're going along, and then we jump to orange, and then we jump back down to green, and then we jump to orange. Okay. Let's do one more. Let's do one that looks a little bit more crazy here. Okay. Same approach as last time. Let's first look to see where we would have horizontal tangent lines. So I'm going to have one here, I'll have one here, I'll have one here, and I will have one here. Okay, so I have these horizontal tangent lines, and what I'm going to do is line up these x values with where I'm going to want them on my derivative graph. Okay, these correspond to x-intercepts. Okay, so I'm going to have, at this first x value, I'm going to have this red dot, and then this red dot, and red dot. And again, my f prime, when I draw it, it's going to have to connect through all of these points. Now, how exactly is it going to do that? Well, let's look in between these first two red points. Again, I'm going to save the ends till afterwards. Let's just look here first. So in that particular spot, our function from the first red to the second red dot, where there's horizontal tangents, this is decreasing. This is going downward. And same thing between the third and the fourth red dot. Okay, our function is also going down here, which means that between these first two green lines and the last two green lines, our function is going to have to be somewhere down here. Okay? So it's going to have to do something like this in order for them to smoothly connect. And again, how far down I go, we're going to talk about that more next week. So we're just going to assume that it's something like that. They're roughly the same. Okay. Now, let's look to see what happens in between this second and third dot here, these red lines. From here to here, our function is increasing. Now it's going upward, and it's going upward for much longer than it was going downward between these other dots. So we're going to have to connect this area for our derivative function with an upside down cup, okay, with a peak, and it's going to be taller. Okay, because our function is increasing for longer in between these x values, between the second and third horizontal tangent points. And now, let's see what happens at the ends. So after the last red dot, our function is increasing, and our function is also increasing in the beginning. So our derivative function, because it's going upward, I'm going to have to be somewhere in my positive y region. Okay, so the only way I can do that and connect to this curve that I already have is if I do something like this. And then that's our f prime. Okay, so one of the main things to remember is when you're drawing the derivatives of a function, wherever your function is going up, your plot will be in the positive y region. Whenever your function is decreasing, your plot will be in the negative y region. And to see where that switch happens, we see where these horizontal tangent lines are. Okay? I hope you found that helpful. I will be posting your quiz for this stuff in a few minutes. Thank you.